Pull into any of the neon-lit lots at the Horizon Japan Festival, and you will see the same strategy on display. It is an arms race of aesthetics and theoretical output. Players pour their credits into heavy, expensive V12 engine swaps and top-speed upgrades. The goal is to maximize the top-line horsepower figure and fill out the on-screen speed rating to boast about a car's potential straight-line dominance. Then, these cars leave the parking lot for the snowy, winding toge runs of Mount Fuji. At the first tight hairpin, that massive, heavy engine pushes the nose wide. The tires break loose, the car plows into the guardrail, and the driver loses total traction. A build designed primarily to look impressive on a menu screen often lacks the mechanical balance required to handle the friction changes of a technical mountain pass. The trap begins with the Performance Index, or PI. The game presents these clean, green stat bars as the definitive measure of a vehicle's speed, handling, and braking capability. But if you crack open that interface, you find that those bars are mathematically misleading. They trick players into buying expensive parts that inflate the visual score, but actively sabotage the car's physical balance. The drivers consistently posting top rivals times rely on a different metric. They build for PI efficiency, calculating exactly how much actual physical grip and thrust they get for every index point spent. Dominating the winter playlist requires looking past these deceptive bars and prioritizing the mathematical variables that drive the car's actual physics. The entire tuning framework rests on one calculation, LE per kilogram, power divided by weight. It measures exactly how much mass every single unit of horsepower is responsible for moving. This diagram visualizes this balance. The central rule of PI efficiency is that removing weight from the chassis is always mathematically superior to bolting on more horsepower. Pulling 100 kilos out of the car shortens your braking distance and tightens your turn-in radius. Adding 100 horsepower to a heavy car just forces it to carry more momentum into a wall. More importantly, shedding weight barely increases your PI score, leaving you room for other upgrades. This ratio dictates the sweet spot for the mid-tier classes. For a B-class sprint, the target is between 0.28 and 0.34 LE per kilogram. Push into A-class, and the ideal window shifts up to around 0.50. A lighter, mathematically optimized vehicle will consistently outcorner a heavy powerhouse, regardless of what the stat bars say. Once the weight is dialed in, players usually fall into the tire trap. They assume the highest-end rubber will automatically yield the best lap time. This bar chart compares the PI cost against the actual grip benefit of different compounds. Equipping full race tires on a B or A-class car consumes a massive portion of your upgrade budget, but the physical return is negligible at those speeds. The mathematical sweet spot is the rally tire. On mixed surfaces and street circuits, it provides nearly identical lateral grip to a sport compound, but costs significantly fewer PI points. By avoiding expensive, low-yield parts like roll cages and oversized front tires, you save points. You can then spend those points on highly efficient parts, like a race differential, which gives you exact control over how the car rotates under braking. Sacrificing perceived visual grip to free up points for mechanical tuning is the ultimate secret to superior handling. With the chassis and grip sorted, the remaining PI points go to the engine, and the type of power delivery you need is dictated entirely by the friction of the road surface. On clean, dry asphalt, the centrifugal supercharger provides a highly efficient boost to the power band. It builds pressure linearly, providing predictable torque that makes the car easier to control through high-speed apexes. But dirt and snow require a different approach. This line graph maps the power delivery of a centrifugal supercharger against an anti-lag turbo system as a car exits a low-speed slide. In the mud, the car is constantly sliding, which drops the engine's RPM. The anti-lag system keeps the turbine spinning even when the driver lifts off the gas. When the throttle reopens, maximum torque is instantly available to claw the car out of the snow. Optimal engine engineering isn't about achieving the highest peak horsepower, but about matching the power delivery curve to the specific friction of the track surface. Take all of that math, apply it to a 1998 Subaru 22B, and bring it back to that snowy toge road on Mount Fuji. While the heavy V12 supercar fights its own weight and plows toward the outside wall, the stripped-down Subaru slides cleanly through the inside. Its 0.42 LE to kilogram ratio allows it to carry speed into the corner.
The rally tires bite into the snow, the race differential precisely rotates the rear end, and the anti-lag turbo immediately puts the power down on the exit. It operates flawlessly because it wasn't built to impress anyone in a parking lot. It was engineered strictly through spreadsheet mathematics. This framework is how you dismantle the winter playlist. The stats the game shows you are irrelevant compared to the actual telemetry of the car. The math holds true across the board. Whether you are tuning a lightweight D-Class momentum car for the city streets or an S-Class aero monster for the highway sprints, PI efficiency dictates the winner. Master the balance of weight, compound efficiency, and power delivery, and you have the mechanical advantage over any challenge the festival offers. Stop chasing the stat bars. Start calculating efficiency and take control of the physics engine.